In this second video about the Zeeman effect, we're going to learn how to calculate the Zeeman energy shift and the energy of the emitted photon. If you are not familiar with those sublevels and the allowed transitions and so on in this diagram right here, I recommend you watch the first video about the Zeeman effect, which I'm going to link in the description down below, because this one builds upon that knowledge. During a transition from a higher state to a lower state, a photon is emitted, and that photon has the exact same energy as the energy difference between the two states of the transition. So without a magnetic field present, we just have this state and this state without any splitting, and the photons emitted by this transition, which we call sodium D2 line, have this exact amount of energy, which is the energy difference between the higher state, double P 3/2, and the lower state, double S 1/2. So in order to find the energy of a photon emitted during a transition between Zeeman sublevels, we need to find the energy difference between the two levels. But how do we actually do that if we have all those split levels? Well, that's where the Zeeman energy shift comes into play. The energy shift, usually denoted as delta E, is the difference between any Zeeman sublevel and its respective normal level without Zeeman splitting. So the Zeeman energy shift of this level right here would be this difference. Similarly, the Zeeman energy shift of this level would be this difference. So if we have the sodium D2 line without any Zeeman splitting given, and we are asked to calculate the energy difference between these two levels, we can simply take this value, add the Zeeman energy shift of this level, because it makes the difference larger, and subtract the Zeeman energy shift of this level, because it makes the difference smaller. The formula for the Zeeman energy shift is this one right here. As you can see, it depends on mj, because we can calculate the Zeeman energy shift for every single one of those Zeeman sublevels. Mj is the magnetic quantum number of the total angular momentum, so these right here. Gj is the Landé G factor of a state, which is calculated using this formula, which depends on J, S, and L. So all the values hidden inside those term symbols. Mu b is a constant, the Bohr magneton, so we don't have to worry about that. And B is the strength of the magnetic field in Tesla, which is given in any problem which asks you to calculate the Zeeman energy shift. So the only thing we have to actually calculate to find the Zeeman energy shift is this G factor. Because mj, we can basically just look it up. Mu b is a constant and b is given. In order to demonstrate how this actually works, we're now going to calculate the Zeeman energy shifts and the energy of the emitted photon for two particular transitions. The first example is the transition from double P 3/2 with mj equals 3/2 to double S 1/2 with mj plus 1/2. That is this transition right here. The second example we're going to calculate is the transition from double P 3/2 with mj minus 1/2 to double S 1/2 with mj plus 1/2, which is this transition. And as you can see, even though this diagram is not drawn to scale, it's just a schematic diagram, you can still see that this difference is smaller than this difference, which means in return that when we calculate the photon energy, this one is going to have less energy than this one. And we're going to get to that result in 3 steps. First, we're going to calculate the G factors for the starting states and end states of our transition. Then we use that G factor and the mj's to calculate the energy shift of each of those Zeeman substates. And lastly, we're going to calculate the photon energy with this formula right here. E is the photon energy without any Zeeman splitting, so this line. Delta E start is the energy shift for the starting state of the transition, and delta E end the energy shift for the ending state. This formula can also be deduced from the diagram above, because recall that since mj can be positive or negative, the Zeeman energy shift can be positive or negative as well. That means a positive energy shift for the starting state is going to make the photon energy larger, and a negative energy shift for the starting state is going to make the photon energy smaller. Similarly, since we're going to subtract the energy shift for the end state, now a negative energy shift will make the photon energy larger, and vice versa. But now let's finally get to work. In order to calculate the G factor, you need to be able to read term symbols like this one. And that's also one of the topics I covered in the first video about the Zeeman effect. So I will treat that as a prerequisite for this one. Double P 3/2 means the angular momentum L is 1, the total angular momentum J is 3/2, and the spin is 1/2. If we now plug those values into the formula for the G factor, we get 9/2 3/2 plus 1 plus 1/2 1/2 plus 1 minus 1 times 1 plus 1. And in the denominator we have 6/2 times 3/2 plus 1. Simplifying this, we get a G factor of 4/3. The term symbol of our end state is double S 1/2, which means we have an angular momentum L of 0, a total angular momentum J of 1/2, and a spin of 1/2. Plugging those into the formula, we get 3/2 times 1/2 plus 1 plus 1/2 times 1/2 plus 1 minus 0 times 0 plus 1, which is a bit redundant obviously. And in the denominator we get 2/2 times 1/2 plus 1. Simplifying this, we get a G factor of 2. In the next step, we're going to use that G factor to calculate the energy shift, and we only have to do that 3 times, because if we take a closer look at these two transitions, we notice that both land on the same ending substate. So we only have 3 different substates we have to take care of. For double P 3/2 with MJ plus 3/2, we have obviously 3/2 for MJ. We have a G factor of 4/3, mu B is a constant, and the magnetic field B. Simplifying this, we get an energy shift of 2 mu BB. For double P 3/2 with MJ equals minus 1/2, we have minus 1/2 for MJ. We still have a G factor of 4/3, and mu BB, which simplifies to minus 2/3 mu BB. For double S 1/2 with MJ equals plus 1/2, we have 1/2 as our MJ, 2 as our G factor, and mu BB, which simplifies to just mu BB. Also notice that while it is true that Zeeman energy shifts are kind of discrete because the angular momentum is quantized, those energy shifts are not necessarily integer multipliers of mu BB, since MJ is usually a fraction and GJ can be a fraction too, so it's perfectly fine to get stuff like this. So now, on to step 3. In order to find the photon energy, we basically just have to plug our Zeeman shifts into this formula. E, which is the energy difference without any Zeeman splitting, was given as 2.1044293 electron volts plus the Zeeman shift of our starting level, which is 2 mu BB in this case, minus the Zeeman shift of our end level, which is this. And since 2 mu BB minus mu BB is just mu BB, we get 2.1044293 electron volts plus 5.7884 times 10 to the power of minus 5 electron volts per Tesla, which is mu BB, times B, which is 3 Tesla, and that gives us 2.1046029 electron volts. For the second transition, we're going to do the same, but now we're going to have to add the Zeeman shift of the starting state of the second transition, which is this one, minus the Zeeman shift of the ending state, which is this one, mu BB. Minus 2/3 mu BB minus mu BB gives us minus 5/3 mu BV, and plugging in the values we get 2.1041398 electron volts. And as we can see, this value is smaller than this value, because here we have 1041 and here we have 1046. Of course, the difference is tiny, like small fractions of an electron volt, and that's why I emphasized that this diagram here is not drawn to scale. But despite that, we can see that this energy difference is smaller than this energy difference, which is exactly the result we got. I really hope you found this video helpful. If you have any feedback or ideas for future videos, please type them into the comments. I promise I'm going to read all of them. Thank you so much for watching, and see you in the next one.